Post-tensioning systems in building construction. In this presentation, you become familiar with the current post-tensioning systems that are used in building construction. We talk about specific features of each system, show you examples of different construction technology, and explore the different construction styles using post-tensioning. Now let us start with pre-stressing. Pre-stressing comes in pre-tensioning and post-tensioning styles. Then I talk about tendons, unbonded and bonded tendons, application of tendons in building construction, we will discuss next, construction options, cost, performance, and building code provisions. Let us start with the pre-stressing. Pre-stressing is done in two ways, pre-tensioning and post-tensioning. The focus of this presentation is obviously post-tensioning in building construction specifically. But the presentation also includes some remark regarding the differences between pre and post-tensioning. Now, in pre-tensioning, the strands, as shown on the right, are pulled first and anchored against stiff, strong abutments. Concrete is cast while the strands remain pulled. After concrete sets, the strand is cut. What is very important is this item. Cutting of strands transfers the strand's entire tension to compression to the cast concrete. I repeat myself, the entire force of the strand, which was held by the abutment, now goes into the concrete. This results in pre-compression of the member from the strands. Now, positioning the strands off the neutral axis, as I have shown here, it will add bending moment in addition to pre-compression. And that bending moment could be beneficial if the strands are off-center the right way. Now, when you come to post-tensioning, strands pass through a hollow duct, as shown on the right. The strands are pulled against the cast member and anchored against it. In pulling the strand, this is important, it is critical to the performance of the member to ensure that the member is free to shorten under the jacking force. In other words, you have a roller here for the member to shorten. Profiling the tendon, as I have shown here on the right, it adds lateral forces, up and down forces, in addition to the pre-compression, and the profile can be selected to be beneficial to the in-place performance of the member. Now, figures C and D highlight the force transfer from tendon to the member in pre- and post-tensioning scenarios. In the pre-tensioning scenario, the force P is in line with the tendon. That is how it works. It is equal, and in the same direction. In post-tensioning, it all depends how the member is supported. In the actual structure, member often is tied to other parts of the structure, or if it is not on a roller at the time of stressing, then you end up with a force F, which is a loss to the support. And here on the right, there will be a, so to say, lack of correspondence between the force in tendon, and which is T, and the precompression. Now what? I lost. Good. Again, in a post-tensioning, the force transfer differs. It depends somewhat on the restraint of the support. If the support is not on rollers, the entire force does not transfer to the member. Some of it is escaping to the foundation, as I show here at the bottom left. In this case, at a section here, the precompression is not equal to the force in tendon because there is a diversion of force here. This has influence on the performance of the member that is discussed in other presentations. It is an important consideration. Now, what about tendons themselves? There are two types of tendons: bonded, shown at the bottom, and unbonded. The pre-stressing strand is the same in both of them. It is 7-wire. In the unbonded system, the 7-wire pre-stressing system is greased and encased in a plastic coating. In the bonded system, more than one strand typically are housed in a sheathing, which can be plastic or metal sheet, and the space between them is filled with typically cementitious grout. The unbonded system, the strand remains detached from concrete that surrounds it in its response in the deformation, but in the grouted system, the strand bonds to the grout, and that in turn to the sheeting and concrete around it, and there is a one-to-one interaction and correspondence between deformation of the surrounding concrete and the strand. Early post-tensioning systems in building construction in 50s were made by strands greased, not necessarily anti-corrosive, and wrapped by paper. They did not work well over time, but from mid-50s to now, there has been a lot of change in improvement. The 1955 version now over the years is transformed into something which is fully encased and protected against corrosion, and also can resist water pressure to a moderate level, about 1 meter 3 feet of water above it. The sheeting options change. It can be metal sheets like what I have on the right, or it can be plastic ducts metal sheet on the left and plastic ducts as shown on the right. Generally, the void is much larger than the strand. So the strand has the option to go a little bit up and down within the void, as you see here. When the tendon is at a low point, as shown here, the strand comes up, touches the upper surface at high point in its profile along the member. The strand will be down. So this change between the centroid of the strand and the duct, shown as Z, is a parameter that is considered in design. Z, as shown in figure A, is allowed in design. Now let us look at the response of these two systems to applied load. We look at bonded system, which I have shown here in A, and in its deformed shape in B. Between the strand and the concrete there is grout. The deformation of the member, like I have shown here in bending, is transferred to the deformation of strand. Note that the strand stretches to this line, which is line of deformation of concrete. The plane sections, so to say, remain plane. The performance is somewhat similar to reinforcement, common reinforcement. In the unbonded system shown in the right in these two, the strand, the deformation of the strand doesn't follow that of the member. If the member bends, as you notice here, the strand doesn't come to the face of the deformed member. So the strand is free to move separately. So the applied load or the strand does not participate in the local deformation. Here we have the image on the left of an unbonded system ready to receive concrete, 4 or 5 strands together. The one to the right is a grouted system. Also, it has 4 or 5 strands, but all encased within one duct. Here, each one is individually encased. The one on the left is an unbonded system ready to receive concrete, and the one on the right is a bonded system in a similar situation ready to receive concrete. On the left we have the stressing end of a bonded system that houses 4 strands, metal duct. Observe here there is a hole to receive grout or let air out. The one on the right is similar, has a similar function. The top shows the live end, again with the vent to receive grout. this with 4 strands, and the image at the bottom shows the dead end of a similar construction. At the left, I have the image of a stressing end of a bonded system ready to be stressed from the left beyond the bulkhead with the tube for receiving grout, and to the right it shows the dead end of the same system where the strands are out of the duct and will bond with the concrete when cast. Outside the US, bonded systems were highly used initially, but as time goes by, unbonded systems are becoming more and more popular. The notion that the bonded systems are more durable, easier to maintain, and easier to change is often presented by the supplier as the advantage to use bonded systems. The underlying reason in the promotion of bonded system, in my opinion, is often marketing, driven by economic advantages that the bonding system has for the firm that uses and builds with bonded system as opposed to on a bonded system. Both systems provide acceptable, good long-term performance when done rightly. Here I have the example of the stressing end and dead end of an unbonded system. Each of these tendons holds one strand. Example of unbonded system in construction, both of them high rises, and examples of a bonded system under construction. Both systems can be used in, I would say, practically any type of building construction. When it comes to relative cost, the bonded system is more expensive than the unbonded system. The hardware, the anchor, is often a proprietary item. You just cannot go to a shop and buy it. It belongs to a supplier, and that somewhat restricts the application of a bonded system for any newcomer in the construction who does not have either a license from a hardware holder or doesn't have his or her own system. The bonded construction is more labor intensive. Cost of post-tensioning varies greatly from country to country. In many regions, the market and the cost of bonded is controlled by a number of local suppliers. Now, the important item to note is this: where labor is expensive, unbonded post-tensioning is advantageous. As an example, in Northern California, 1 unit weight, 1 kilogram or 1 pound of unbonded post-tensioning assembled in place, ready to receive concrete, costs essentially the same as 1 unit weight of rebar. 1 kilogram or 1 pound of post-tensioning is essentially the same as 1 pound of rebar when in place. The reason is the cost of labor in a post-tension unbonded construction, the way it is done in the US, the total weight of the reinforcement for a given project is much less than if it is not post-tensioned. And this brings the total cost of labor down. So since the total amount of pre-stressing and rebar, I am repeating myself here, per unit floor area is less for post-tension designs, post-tensioning can be cheaper than the alternative conventionally reinforced floor where labor cost is high. And again, this is the same thing that each unit weight in. Now this is about the contribution. Each unit weight of post-tensioning, when used efficiently, provides 4 times more strength than a unit weight of rebar. That is why it can substitute 4 times more rebar when safety is a consideration. In many regions, there's the practice of adding mesh reinforcement, as I have on the bottom, on the top right. The mesh reinforcement is more, as I see it, a convention as opposed a requirement. I know that in some countries it is a requirement in the code, not in the US and not practiced in the US. Now coming to performance, first the service performance. There's important indicator or a strong indicator is the experience, the observation of the inhabitants of a bonded building or an unbonded building as far as performance is concerned. Over the last 70 plus years, thousands of buildings of different configuration have been built in the US using unbonded tendons. Most have been in service over half a century. The observation of the performance of these buildings overrides speculations of how the buildings reinforced with unbonded tendons would perform in service. There are thousands of them over 70 years of age. Look how they have performed. The performance has been satisfactory, and that is the reason more of it is being built. From standpoint of users of a building, there is essentially no noticeable difference in the occupancy experience, whether the building is bonded or unbonded. A question that is often raised is, what about if there is a need for repair? If, for example, we want to make a large opening in the floor. This example shows that it is practical for unbonded tendons too to make a large opening in the middle of a panel where strands in this example have been crossing both directions because it is a waffle slab construction, about 4.42 by 3.5 meter opening made in the middle of a panel that is 14.5 by 11.5 feet, and it was done, the strands along the cut were captured and re-anchored at the edge of the cut. So it is possible. It is possible, it is practical, but it requires special skill, a little bit more complex. It must be engineered with professionals conversant with post-tensioning. there are additional, obviously, considerations because of the force in strand. Now, cutting pre-stressing strand is more detrimental to the safety of the structure than cutting a non-pre-stressed reinforcement of the same cross-sectional area, because at ultimate limit state, the pre-stressing strands provide 4 times more resistance than a rebar of the same cross-sectional area. What is important also is precompression. Image on the right shows partial area of a floor slab. Tendon is pulled at the ends and the precompression spreads into the slab. Now, if you have an unbonded system shown in this diagram and it is cut somewhere in the middle, the entire precompression is lost. The diagram at the top shows the precompression, and the strand becomes useless over its entire length. This is the argument often presented by suppliers in favor of bonded post-tensioning. When a bonded post-tensioning for repair or any other reason is cut, as shown here on the bottom right, the precompression over the region immediately surrounding the cut is lost, but the remainder of the structure will retain its precompression. The cut will have no tension, but the tension will remain in the remainder of the strand because of the bond of the strand with the concrete. So in effect, the contribution of bonded tendons to local strength is analogous to non-pre-stressed reinforcement. So safety. Bonded and unbonded systems can be designed to meet the safety requirements of the code to the same level. There are several differences, however. That is somewhat repetition of what we had in the previous slide. Unbonded tendon damage covers the entire length. It is a loss over the entire, whereas a loss of bonded tendon due to damage is local. This is what we had in the previous example. Now, this is a consideration which I think is very important, and that is support restraint. Post-tension members, like I have in this slab, are often attached to other members, like in this case a column up and down. At stressing, the supports restrain the shortening of the member to some extent, in particular if this is the first elevated slab and the column is tied to the foundation. In this case, some of this precompression, which is intended to go to the slab, will be diverted to the support. The member does not shorten fully because of the restraint. Now, this restraint and diversion of the force impacts the safety as well as the, so to say, serviceability of the member. It can lead to cracking from shrinkage, but that is more a visual item and can be repaired. What is more important is the reduction in strength as a result of loss of precompression, and that is something which is handled in greater detail in another presentation of this series, which talks about the significance difference in performance of bonded and unbonded as a result of restraint. It is given in the reference at the end of this presentation. In short, what was covered in this presentation? I talked about pre-tensioning and post-tensioning, talked about unbonded and bonded tendons. We talked about the response to load. We talked about construction options, bonded systems, unbonded systems, relative cost, and performance in service and safety. Thank you for listening. The presentation made in this package was from one of the chapters of this book shown here. And here a disclaimer. Thank you and have a good day.